For today's presentation, I'm going to take you through some of the general groupings of detectors, some of the fundamentals like Beer's law, and then a brief overview of the main detectors used for liquid chromatography, such as UV-Vis, the photodiode array, the fluorescence, refractive index, mass spectrometry, evaporative light scattering, and a few others as well. If at any moment during the presentation you have a question, please don't hesitate to submit it in the chat. I will do my best to answer questions as they come up, but if not, we will have some time at the end for questions for sure. For those of you who attended previous presentations, this graphic should be familiar. In the prior talks, we discussed general fundamentals of liquid chromatography, the purpose of the different parts of the hardware, and a deeper dive into how to select a column for your analyses. Today, we're going to focus on detecting the analytes through a variety of modes. The detector or the detectors that you choose will be dependent on what you are trying to detect and at what levels of concentration. I'm going to say that again because that's kind of a really important key take-home statement. The detector or the detectors that you choose will be dependent on what you are trying to detect and at what levels of concentration. The detectors can be grouped into two classes, bulk property and solute property detectors. Bulk property detectors are going to measure a difference of a physical property between the solute or the analyte mixed with a mobile phase to that of the mobile phase by itself. The detectors are considered universal detectors, but tend to have poor sensitivity and limited range. They are affected by small changes in mobile phase composition, preventing their use in gradient dilution. Solute property detectors respond to physical or chemical property of the solute, being ideally independent of the mobile phase. In practice, however, complete independence of the mobile phase is rarely achieved. But the signal discrimination is usually sufficient to permit operation with solvent composition changes throughout the analysis. They generally provide high sensitivity and a wide linear response range, but as a consequence of their more selective nature, more than one detector may be required to meet the demands of the analytical problem. As we begin to decide on the specific detector we want to use, we have to bear in mind the needs of our analysis and the limitations of the detectors themselves. This is a good starting point of some of the criteria we want to think about. For example, sensitivity tells us the minimum change to our signal that is required that the instrument can detect and is expressed by units of concentration of the analyte that you are trying to detect. Also, does the detector fit within the needs of the analysis? We will speak to this in greater detail on the next slide. Selectivity, on the other hand, addresses the ability of the detector to distinguish one analyte from another. Another important criterion to bear in mind is determined by whether or not you need to collect the sample after analysis. Some detectors will consume the sample in the process of detecting the analyte, while others will leave it intact. On the detector side, we want to think about sensitivity in two ways. The limit of detection, which is some measurable response above the noise. Most commonly, it is 3 times above the noise, and the limit of quantitation, which is a response that is greater than that of the detection limit and approximately 10 times of the noise. It is important to note that 3 and 10 are commonly used, but different regulatory bodies might use different criteria for the specific analysis you might be doing. The limit of detection is sometimes referred to as the minimum detectable limit or the minimum reportable limit. The linear dynamic range is going to be the range of concentrations at which the signal gives a linear response. This is important to keep in mind when making your calibration curves and developing methods. If you fall outside of this range, it will not be possible to relate your signal response to a specific concentration. Noise refers to how the raw signal oscillates from the baseline, and drift is how the baseline changes over time. Some detectors have really low values for drift, but others require some form of calibration before continuing analysis. It is important to measure noise and drift of your detector at regular intervals to ensure that you're within the specifications. The detectors we will cover in today's presentations are the ones you will most commonly encounter, which are UV-Vis, fluorescence, refractive index, mass spectrometry, and evaporative light scattering. There are a few other detectors that we will touch on briefly, but we will not cover all the detectors that are available. Before we get into the detectors themselves, we need to touch upon the Beer-Lambert law, which states that the direct relationship between the absorbance of light and the concentration of an analyte in solution. The sample cell is shown on the slide with some green sample in it. As the light travels through the sample, we absorb some light. Aside from the absorbance, which is measured by the instrument, we also need to know the path length, or B, and the molar extinction coefficient, which is given to us by the Greek letter epsilon, as we can see in our particular equation. However, if we measure the absorbance at different concentrations, you should end up with a linear curve with the signal being on the y-axis and the concentration on the x-axis. If we fit a line to these particular points, the slope represents the path length and the molar extinction coefficient. Because it is a direct relationship, if we measure how much light is absorbed, we can then calculate the concentration within a particular range. The curve on the slide represents a measurement of 5 different concentration points. The line is the best fit line. And if we measure an unknown sample's absorbance, we can use this best fit line to convert the response to a concentration. This is the fundamental principle that is used for transforming the signal of an optical detector, such as a UV-Vis detector, to a concentration value as a result for the analysis. The first detector we will look at are UV-Vis based detectors. They measure the ability of solutes to absorb light at particular wavelength or wavelengths in the ultraviolet UV or the visible Vis wavelength range from around 190 to 790 nanometers. In general, the mobile phase has a limited measurable response within these ranges, and gradients can be used. When light of a certain wavelength is directed at a flow cell, the substance inside the flow cell will absorb the light. As a result, the intensity of the light that leaves the flow cell is less than that of the light that enters it. An absorbance detector measures the extent to which the light intensity decreases, i.e. the absorbance, after the sample interacts with light. It can be collected or disposed of, making it a non-destructive detection method. There are 3 types of UV-Vis detectors we want to touch upon. A fixed wavelength detector, in which the absorbance of only one given wavelength is monitored. This is achieved by using a fixed optical filter, typically 254 nanometers is quite popular. And to change the wavelength, the filter needs to be changed manually. Then we have variable wavelength. A single wavelength is monitored, but any wavelength in a wide spectral range can be selected. The wavelengths used can be fixed at specific wavelengths. They can be selected programmatically throughout the method, or the detector can scan across a range of wavelengths over time. And finally, we have a photodiode array detector, where a whole spectrum across a wavelength range is acquired at every particular time point. Here we have a general schematic of the variable wavelength UV-Vis detector with the key components shown. We start with our light source. Deuterium lamps are used for UV analysis, and tungsten lamps are used for visible wavelengths. The light is then passed through a slit, and it strikes the movable grating, refracting the white light. The slit only takes a beam of the light in the direction of the grating. Moving the grating determines which color of the light makes it out of the exit slit to go interact with the analyte in the flow cell and finally be detected by the photodiode. The main component of this type of detector is the grating itself, as it determines the wavelength of light that will interact with the sample. Only one wavelength of light reaches the samples. The others never reach the sample. Selection of the analytical wavelength, the wavelength that will interact with the sample, can be controlled programmatically. This is the analysis of some common preservatives found in personal care products. The top chromatogram shows a separation of these compounds at 220 nanometers. But I want to draw your attention to peaks 1 and 2, which are labeled, 1 being 2-phenoxyethanol and 2 being ethylparaben. The bottom chromatogram is the same separation, but we monitored the absorbance at 254 nanometers. Notice that peak 1's absorbance changes significantly between the two wavelengths. In this case, 220 nanometers is more sensitive at detecting the presence of 2-phenoxyethanol. However, if we look at the signal response for peak 2, ethylparaben, we see a slight increase in response. The response for peak 2 is greater at 254 nanometers than 220 nanometers. The other compounds also have a greater response at 254 nanometers. However, their change is not as marked as that of 2-phenoxyethanol or peak 1. This is why selecting the appropriate wavelength is important, because it can have dramatic effect on your results. So how do we go about resolving this particular issue? If we can control the wavelength selection programmatically, we can tell the instrument to monitor one wavelength for a period of time, and then switch to another wavelength after that. This is the same analysis of the preservatives I showed you on the previous slides. The analysis began monitoring at 220 nanometers, but after around 1.5 minutes, the wavelength shifted to 254 nanometers. This results in getting the best response from both wavelengths and all in one chromatogram. The next type of UV-Vis detector we are going to look at is the photodiode array detector, or PDA. Sometimes you might hear it be referred to as a diode array detector or a DAD. The main difference between this detector and the variable wavelength detector is the location of the flow cell in relation to that of the grating. The cell, in this case, is right after the entrance slit, and all the wavelengths of light from the source go through the sample. After going through the sample, the light then strikes the gradient, refracting and then hitting an array of photodiodes. This results in a full spectrum being acquired at each time point that the data is acquired. The PDA offers up a valuable trove of information. So far, for all the techniques discussed, will give us a retention time and peak area, but the UV-Vis spectra that we get at a given point, like the one shown here above this chromatogram, allows for a host of other information to be that we can utilize. We can use the spectrum to form a spectral library, which we can compare unknown samples to help identify them. The spectra can show us what is the maximum wavelength of absorption to help optimize the method. It allows for a peak purity calculation to determine if analytes are co-eluting, and PDA is also generate a contour plot. So this is what a PDA contour plot or a contour map looks like. It is a two-dimensional representation of three-dimensional data. On the x-axis is time, the y-axis is wavelength, and the third axis is represented by color is the signal of the detector, with a gradient of blue to red from low to high, respectively. This particular contour plot is the separation of our universal test mixture, which consists of 5 compounds: toluene, ethylbenzene, isopropylbenzene, T-butylbenzene, and anthracene. You can see that the intensity signal at around 205 nanometers for the first 4 compounds is so great that it saturates the detector, hence that white color that we're seeing on the color map. We can also see that anthracene, the 5th compound, does not have any absorbance at those wavelengths either. However, all the compounds have a signal around 254 nanometers. So we can use that for our analysis of all 5 compounds without worrying about saturating the detector or without having to dilute the sample further. The contour plot is an invaluable tool for method development and troubleshooting. To summarize, UV-Vis detectors offer great sensitivity and selectivity while allowing for gradient mobile phases. They can provide qualitative information about the identity of analytes using the spectral data and are non-destructive to the sample. Fluorescence detectors work on similar principles as UV-Vis detectors, but with some key differences. In this case, we are still utilizing a light source, most commonly here a high-energy xenon lamp. Selecting a wavelength in the same way as the variable UV-Vis, we're going to label this our excitation wavelength, and then the sample also absorbs the light. However, the sample in this case takes the light and undergoes electronic transformation and emits light again at a longer wavelength. This requires that the sample be able to convert the absorbed light into emitted light, which many compounds cannot do. This makes this method of detection highly selective because we want to measure the generated light. The detector is not on the optical path of the emission source. This helps to boost the sensitivity of the method when using fluorescence. We always need to specify 2 wavelengths. So the wavelength selection can be achieved by using fixed filters for both of the excitation and the emission, or by using monochromators, either just at the emission or both the excitation and the emission. Like UV-Vis detection, fluorescence detection is also non-destructive and can be used with gradients. Some of the general rules that we want to keep in mind for fluorescence are that fluorescence occurs at longer wavelengths than absorption. The excitation spectrum is identical in shape to the absorbance spectrum. The emission spectrum is the mirror image of the longest wavelength absorption band. A pure compound exhibits a single emission spectrum, regardless of the excitation wavelength. And the brightest emission is obtained by exciting in the strongest absorption band, since more light is being absorbed and converted to fluorescence emission. The Stokes shift is a measurement of the distance between the last band of the absorption, or the excitation, and the first band of the emission. And I'm going to show you what that looks like in the next slide. So this is the fluorescence spectra of anthracene that demonstrates the rules we discussed previously. We see that the emission occurs at longer wavelengths than the excitation. So the excitation here is in black and the emission's in red. The emission and the excitation are mirrors of each other. And there are 2 points where we would measure the Stokes shift. And let me just pull those up here. I'm going to point to them on the screen. So just go ahead, pay attention. I'm going to mark this little black. There's the black point, and then let me put the other one. This is the red point over here. So those would be the 2 points where we would measure the Stokes shift, and we would measure that in nanometers. Another thing displayed on this particular spectrum is phosphorescence, which occurs when the sample undergoes a more complex electronic transformation. Fluorescence detection focuses on fluorescence and not phosphorescence most commonly. The easiest way to differentiate the two is by how long the emission occurs after the excitation. Fluorescence will cease very shortly after the excitation ends, whereas phosphorescence can last for many seconds afterwards. Those glow stars you may have had in your kid and as a kid on your bedroom ceiling are a good example of phosphorescence. Other key points to keep in mind when doing fluorescence detection is that fluorophores can have a simple or complex absorption spectra. So knowledge of the wavelengths and the strengths of the absorption bands is crucial. Excitation of a pure fluorophore in any of its absorption bands will produce a single color emission band. Often the longest wavelength absorption band is used for fluorescence excitation, which yields the greatest selectivity, but not necessarily the greatest sensitivity. So which molecules fluoresce? Typical molecules that will be amenable to fluorescence detection will have lots of conjugated pi electrons, multiple ring structures that are coplanar. As mentioned earlier, not many compounds are natively fluorescent or can be made to fluoresce by derivatization, only about 20% or so. Functional groups also have an effect on fluorescence, with electron donating groups such as hydroxyls and amines increasing the fluorescence, and electron withdrawing groups like carboxylic acids decreasing the fluorescence. Because the excitation and emission of a fluorophore occur at characteristic wavelengths, it makes fluorescence detection very selective. We can utilize this to detect individual components in a mixture by selecting the appropriate excitation and emission wavelengths. We can make the measurements in a variety of ways. We can measure the intensity versus time at a fixed excitation and emission wavelengths. We can do a wavelength program where specific excitation and emission wavelengths are changed at specific times, or we can do scanning of either the emission or excitation wavelengths to glean other types of information. Here's a chromatogram of fluorescence detection of some polycyclic aromatic hydrocarbons, or PAHs, that demonstrates the detection of conjugated planar structures like pyrene. Fluorescence detection in this case is used to achieve improved sensitivity over other detection modes, such as UV-Vis, which is also used in this particular type of analysis. To summarize, fluorescence detection provides excellent sensitivity for those compounds that do fluoresce, and great selectivity by adjusting the excitation and emission wavelengths. It affords the use of gradients and is not destructive to the sample. Refractive index detectors are bulk detectors that measure the difference in optical refractive index between the mobile phase and the sample. In order to do this, there has to be a real-time reference of the mobile phase. The flow cell in this case has two compartments, a reference cell and the sample cell. The reference cell needs to be purged with mobile phase prior to the analysis to contain the same composition that the mobile phase will have when we're going through the sample analysis. When the flow is directed through the sample cell during the analysis, light passes through the two cells and is refracted differently when the sample is present in the mobile phase. The sample is not destroyed during detection. Because the reference cell is needed, isocratic elution can only be used, so no gradients. Because the physics of the detection scheme, this mode lacks sensitivity and is therefore reserved for analytes that do not absorb UV-Vis light or fluoresce. For example, carbohydrates and hydrocarbons are good examples of analytes that are typically used for refractive index detection. Some factors that can affect the response of the detector are changes in concentration, changes in the mobile phase, whether in the sample cell or the reference cell, pressure, and temperature. Most refractive index detectors generally contain a heater for the sample cell or for the sample and reference cell to maintain temperature constant, slightly above room temperature. Dissolved air in the mobile phase can also affect the measurement. Drastic changes to the ambient conditions that the instrument, where the instrument is present, will have a negative effect on the quality of the analysis. The reference cell typically needs to be purged daily to ensure that the mobile phase composition in the sample cell and reference cell are equivalent to each other to ensure the quality of your analyses. This is an example of two refractive index chromatograms looking at sugars and maple syrup that show the detection of carbohydrates that would not generally be detectable with the previous two detection modes that I have mentioned. So on the top one, we have a sugar standard with fructose, glucose, sucrose, and maltose. And the bottom is a spiced apple maple syrup that's overlaid with a standard. And we can see that the main component of that particular maple syrup is sucrose. There's a little bit of fructose and a little bit of glucose, but there is no maltose present. To summarize refractive index detection, it is a universal detector, but it suffers from poor sensitivity and not being able to use gradient dilution. It is extremely temperature sensitive, but it is not a destructive method. This type of detection method is also sometimes used in higher prep scale work, where you're passing through extremely large concentrations of sample. And so therefore, you're not necessarily worried about that sensitivity aspect. Mass spectrometry is the next mode of detection I want to discuss. It is widely popular, but far more costly than the methods I previously mentioned. It is a destructive method where the analytes are ionized and measured by their mass to charge ratio. There are a variety of sources that can be used for ionization depending on the goal of the analysis. This mode of detection can provide both qualitative and quantitative information with excellent selectivity and sensitivity. There are a variety of mass analyzers to achieve the detection, but most commonly used in liquid chromatography are quadrupole and time of flight. The details of how each of these mass analyzers work are beyond the scope of this presentation, but we will be addressing that in subsequent presentations. With mass spectrometry's great sensitivity and selectivity, it is a valuable detector to couple to liquid chromatography's powerful separation ability. Before the sample enters the mass analyzer, it needs to be ionized and in the gas phase. Two of the main methods for ionization for liquid chromatography include electrospray ionization and atmospheric pressure chemical ionization. Combining these two allows for many weak and strong polarity compounds to be analyzed. The resulting chromatogram generated is a summation of the signal response of the mass spectrometer at any given point. That means that each peak in the chromatogram can generate a mass spectrum to give more refined structural data. The more information with enhanced selectivity and specificity and sensitivity can be achieved by using a tandem mass spectrometer. In essence, the data generated by a mass spectrometer is similar to that of the contour map for the PDA, where we have 3 axes of data, except in this case, we have time, mass to charge ratio, and intensity. All this information can help resolve very complex mixture of analytes. This is an example of a chromatogram from a triple quadrupole mass spectrometer. As you can see, it looks much busier than the previous chromatograms I've shared, but that is because of the density of information here is much greater. Each color represents an individual pesticide in a T sample, and as you can see by the title, there are 400 pesticides present in this particular chromatogram. We can get concentration information and structural confirmation for each of the 400 pesticides that are present within this particular analysis, and all under 17 minutes. And this is the strength of the information that tandem mass spectrometry affords for being a detector for liquid chromatography. The next detector I want to touch base upon is evaporative light scattering detector, which is a bulk property detector. It is not as a universal detector as refractive index, but it is used in a similar way. It provides more sensitive detection and a stable baseline. The analytes do not need to be chromophores in order to be detected. The column effluent is nebulized into a heated drift tube and then quickly evaporated to form fine particles. These particles are then irradiated with a laser beam, and the scattering is measured. This mode of detection is destructive to the sample. There are other detectors available for liquid chromatography, but are not as common and for more niche applications. The electrochemical detector functions on the resulting current from a redox reaction of the analyte at a suitable electrode. This requires specific types of analytes, making it very selective. It is typically used for amines and carbohydrates with very good sensitivity. The conductivity detector requires ionic samples, but suffers from poor sensitivity. This mode is most commonly used in ion chromatography. Other detectors included Other detectors that you can use for liquid chromatography include charged aerosol, chemiluminescence, optical rotation, multi-angle light scattering, radioactivity, and many more. To begin to wrap up, the most common detectors are listed here with some of the major key points to remember. So the three ones that we really want to take away from this particular presentation is the refractive index detector, UV-Vis, and fluorescence. And remembering that refractive index is going to be a universal detector that can give us approximately milligram sensitivity for our sample concentrations. It is extremely flow and temperature sensitive, and we are limited to only using isocratic methods for our sample analysis. The most common samples that we're typically looking at are going to be non-UV absorbing samples, such as hydrocarbons, carbohydrates, and aliphatic amines. UV-Vis, in this case, which we're looking at both the fixed, the variable, and the photodiode array, are extremely selective and almost universal detectors for liquid chromatography. They give us excellent sensitivity down from microgram to nanogram, flow and temperature insensitive. So that means that we can use gradients for these types of analysis. And mostly we can take a look at most compounds, particularly unsaturated aromatics and carbonyls. Fluorescence is the third detector, which is extremely selective. We can get even better sensitivity from nanogram to picogram. And again, just like UV-Vis, it's also flow and temperature insensitive. So we can use gradients as well. The only issue here is that the types of samples that we can look at are limited to those that exhibit fluorescence, mostly conjugated aromatics, polynuclear compounds, and those and catecholamines. To summarize the whole presentation, we went over how to classify the detectors as either bulk property or solute property. We discussed some of the general considerations for choosing a detector for HPLC, such as the limitations of sensitivity, selectivity, and whether or not you need to recover the sample after the analysis. Remember that there are a variety of detectors that are available for use with most liquid chromatography systems. And the selection of the right detector is highly dependent on the goals of the specific analysis and the analytes themselves. Finally, the three most common detectors that you're going to encounter are usually going to be UV-Vis, fluorescence, and refractive index. Now, mass spectrometry is also listed below because it's, because it's commonly found coupled to liquid chromatography systems, it kind of falls under a whole different price range. So we're not really going to focus on that one as much.